Okay, okay, let's see the depth first search. So for the depth first search, we are using another strategy. So we are gonna from the root, we are gonna decide a direction, and then we are gonna go deeper to a node, and then if there's another way to go even deeper, we follow that way. So we want to from the root, we want to go deeper, go deeper, go deeper, and eventually when we have to stop, and then we step back by one step and see is there another direction that we can go even deeper. And then if there's no way to go, we step back, and then we may step back again and see if there's another way that we can go deeper. So we also always want to pick a direction, and then we want to go deeper inside, unless we have to stop and then we do a step back. So this will be our strategy. And we are still going to use the same coloring. The white means, well, a node hasn't been discovered yet, and gray means this node has already been discovered, but we haven't finished exploring that yet. And then for the black, it means that node has already been finished visiting. Okay, and this is the node of the depth first search. The very first part on the left side. Okay, so the line 1, 2, and 3. Well, that is the first iteration that we color all the nodes to be white. And then for the pi, we have seen that before. The pi means the parent. So the parent of each node is set to be a nil. And after that, we will initialize a timer, and this timer will show us will keep help us to keep a record of the time on when do we start visit a node and when we finish visiting the node. And after that, and for each of the vertices U, and then if its color is white, and then we want to do a Dfs visit, and this brings us to the second function. So for the Dfs visit, and the first thing we want to do is we color that into gray, because we see a white node and then we start to visit that node, so we are going to change the color to gray. And after that, we increase the timer by 1 because we are visiting a new node. And for du, we are assigning the time to the du, and du means the discovery time. So it's keep a record on when the node is discovered. And after that, for each of the adjacent node of the current node u, if the node v is a white node, and then we are going to set u to be the parent of the v, and then we are going to do the Dfs visit of the v. So this is a recursive process, right? And after that, after finishing visiting u and and v and all the adjacent nodes v, and then we are going to change the color of the u to black, and then we increase the timer again, and then we assign that to the fu, saying that is the finish time. Well, the algorithm itself might be a little bit dry, and before we move on and see the examples, I have to spend some time to discuss some of the details. So the number one question, will all vertices eventually be colored black? Okay, so you have to think about this. There is two iterations that we are trying to find all the white nodes. So the first iteration is here. So in this iteration, well, for each of the nodes, and if it is white, and then we will do a Dfs visit. So this iteration guarantees that we will visit all the vertices in the graph G, right? And the second one, this iteration is visiting all the adjacent nodes of the node U. And then if the color is white, and then we are going to do a Dfs visit. So there are two places. So for the one on the right side, it only visits the adjacent nodes of the current node U. However, the left side, we have an iteration that guarantees we will visit all the nodes in the graph. And so it is safe that for each of the y node, and it will receive at least one visit. And after we visit that, and eventually after we call the DFS visit, eventually that node will be colored black. So to answer this question, will all the vertices eventually be colored black? And rest easy. Well, the answer is yes. Well, it doesn't matter. We are going to create, if all the components of the graph are connected, or there are several isolated components of the graph. It doesn't matter. It will guarantee that we will visit all the nodes. Okay, and the second one, that is a fun question. I may need to use my pen again. So what is the running time? So if you see this one, that is OV, because we are visiting all the nodes, all the vertices, and then for each of the vertices we are visiting once, right? And this one, O1 for sure, and this one is another iteration, so that is a OV here. So we are going to visit all the vertices again. Okay, and then we have a recursive call here. So inside of this OV, there might be another time complexity of the DFS visit. So we have to figure out what is the time complexity of the DFS visit. So this is a O1 and O1, O1. And then for this one, if we are considering this graph to be a full one, and then the upper bound of the adjacent u, which is the iteration we are going to run for this for loop, will be for this part. This will be a OV. So this is the upper bound, because for each of the nodes, the number of the adjacent nodes will have the upper bound to be V, right? So this iteration is a OV, and then O1, O1. So if we add everything together on the right side, we will have a OV, and then plus 5, which will give us a OV, right? So this means if we move this OV to here, and this is a OV inside another OV, so we will have a OV square, and then plus O1, and then here we also have a OV, right? So OV plus OV square, and then plus a O1, so this will give us a OV square. Okay, so this is a very quick analysis. I would say this is the basic analysis of the algorithm, but it is not the tightest bound. We can't say that it's wrong, because OV square is indeed correct, but this is not the tightest bound. So, and to figure out the tightest bound, what we can do is, we can try to figure out how many times we are going to visit each of the edge and each of the DFS visit. So for the DFS visit, we are only going to call that on each of the white node, right? So if we see a black node or a green node, we won't call that anymore. So we will only call the DFS visit once for each of the node. Because the second time we see that node again, that node might be gray, might be black, but this node won't be white anymore. The point is, for the DFS visit, for each of the nodes, we will only call the DFS visit once. Okay. And then how about the edges? So for each of the edge, and then there are two vertices, U and V, for example. And then for the U, we may visit that edge, and then from the V, we may visit that again. This means, if it is an undirected graph, for each of the edge, we will visit that twice and twice only, right? So if we think about that, so for each of the v, we will only visit each of the vertices once, and then for each of the edge, and then we will visit that twice at most if that is a undirected graph. So if we want to add those two together, and then what is that? That is a OV plus E. Okay, so that is a tighter upper bound. So for this one, the upper bound is OV square, and that is not wrong, but that is not the tightest possible one. And the tightest possible one should be OV plus E. Okay, so that is a very dry analysis of the DFS algorithm, and let's take a look on an example. So we have a directed graph. Remember, this one is directed, and then we want to start the DFS from this node. So the first step, we see the root, and then, well, we remember we are using D and F. D is the time when the node is discovered, and F is the time when this node has been finished. Okay, so from the D, well, it is 1, and then we want to select one direction that we want to go deeper. So I decided that I want to go to the left side, and then I discover the second one, and then the discovery time will be the 2, and then is there any way that we can go deeper? And yes, we can go deeper. We find this one, and then that is 3. Okay, so the next one, I have a question. Can we go with this path? So can we go from here to the source vertex or to the root of the tree? So is this the right way to go? The answer is no, because when we are doing the DFS, we are only discovering the white vertices. Okay, so we can't go that way. And is there any way else we can go? The answer is no, right? So we have to say, okay, this node, I have finished visiting you, and there's no way to go even deeper. And then when there's no way to go even deeper, what do? We have to step back. So we go back to this node and say, okay, I have visited one direction. I have explored that all the way to the end, and then which way else can I go? And then I can go here. So I discovered a new node, and then the discovery time is 5. And then from this node, unfortunately, we can go nowhere. So we finish visiting that node, and then we come back again. So for this node, and we have no further way to go, so we have to color that black, and then we step back to the root, and then the root will show us a new direction to go deeper. So we can go here. So from this node, we can go to this one. So this is the new white node we discovered, and from this one, we can go here, but this is black node. We have already explored that. So from this node, we can go no other vertex. So we have to finish, and then we have to finish that. And after that, we finish this one because there's no new white node, and we have finished this one. Okay, so this is the first step. We finish all the possible nodes starting from the source vertex. But are we finished? The answer is no, we haven't. Why? Because, well, here, for each vertex, U belongs to the vertex of the G, right? So there are still white nodes we have to visit. So even though here we have finished all the possible nodes belongs to this tree, we haven't finished yet because there are still 2 more white nodes. Say we want to start here, and then the start time will be a 13, and then we have to go this way, and that is the only white node we haven't explored yet. So the start time will be 14. We finish that one, and then we finally finish this one. So if this is a process that we can do a DFS, and well, if you take all the red edges, and guess what? You will have 2 trees. So the first tree has the root of this one, and then the second tree's root is this one. So we have two trees, and using those two trees, we can finish visiting all the nodes possible in this graph. Okay, so that's it, and we have a little bit more in this lecture, and I will see you in the next video.